Good morning, everyone. This is Payavala Bhavgna from Institute of Aeronautical Engineering, IARE. I am from the branch Computer Science and Engineering from Section A. My roll number is 24951A0559. Today, I am here to explain the topic estimating the specific heat capacity and heating of electronic sensors and devices from the subject elements of electrical and electronic engineering. Now, let us quickly dive into the introduction part. Introduction to specific heat capacity. Specific heat capacity is a material property indicating how much heat energy is required to raise the temperature of a unit mass by 1 degree Celsius. Understanding this property is crucial for the thermal management of electronic devices. In electronic applications, efficient heat dissipation can prevent damage and improve performance. Here we have an example. The heat when we place pan and it has a hot substance in it. Example, let's take soup, and you have kept two spoons. One is metal one and the other is wood one. A metal spoon used to stir your soup will heat up a lot faster than the wooden one, right? Because both spoons receive the same amount of energy. The amount of energy required to increase the temperature of an object is dependent on the material. We all know, like, metal materials are quickly adapted to the heat surrounding, unlike wooden ones. Importance of thermal management. Thermal management ensures that electronic devices operate within safe temperature ranges. Excess heat can lead to performance degradation and reduce the lifespan of devices. Proper design and implementation of thermal solution can enhance reliability and efficiency. Now, here we have a thermal interface, and the upper part is known as heat sink, and the light pink part is package. This is heat source, and without TIMs, without filling the air gaps, the graph goes like this, and with the filling, it is like that. The blue substance is the thermal interface pad or sheet. Surface temperature of the packaging is this graph. Factors affecting specific heat capacity. The specific heat capacity of materials varies based on composition, structure, and phase. Temperature and pressure also influence the specific heat capacity of substances. Understanding these factors helps in selecting materials for electronic components. Now, here we have the example that we got a copper block here and an aluminium block and also water. Now, we all know that the specific heat capacity of copper is 390 joule per kilo, and aluminium specific heat capacity is 910 kilo per joule per kilo, and the water's is highest, which is 4200 joule per kilos. Lower heat capacity, lower specific heat capacity warms up and cools down quickly. So we all know that the metal gets easily warmed up and easily gets adapted to the heat, and uh, and it takes much less energy to change its temperature. Once it is heated up, it takes very less time to energy to change its temperature. Same with aluminum, but it is since it has a greater specific heat capacity than copper. It is like medium. And then we have water. Water heat capacity is highest and it is 4200. Higher specific heat capacity warms up and cools down slowly. Like water takes a much longer time to warm up than a metal. When you place a pan and you try to boil water on a stove, it takes a lot of time compared to the time when you place a wooden block in on a fire. Measuring specific heat capacity. Specific heat capacity can be measured using calorimetry, where heat transfer is quantized. Differential scanning calorimetry (DSC) is commonly used for precise measurement. Accurate measurement is essential for modeling thermal behavior in devices. Heat transfer mechanism. Heat transfer in electronic devices occurs through conduction, convection, and radiation. Each mechanism plays a role in how heat dissipates from the device to the environment. Understanding these mechanisms is vital for designing effective cooling solution. Methods of heat transfer. Now, when we place a pan and you try to boil or cook something in it, the handle gets heated too, right? That is known as conduction. And the heat or the source is known as radiation, and the process going inside the pan is known as convection. Now, conduction means the movement of heat within an object is called conduction. Conduction also occurs when objects are touching. Radiation. Radiation is the transfer of energy through electromagnetic waves. And convection is nothing but the transfer of heat from one region to a field to another due to the movements within the fluid is called convection. Heat generation in electronic devices. Electronic devices generate heat primarily due to resistance in conductors and semiconductor processes. The power dissipated as heat can be estimated using the formula P equal to I square R. Managing this heat generation is critical for device reliability and performance. Now we have a diagram here. This is known as alternating flux, and this is the working coil. High frequency alternating current are passing through these edges. Eddy current due to the influenced voltage, and the work piece is this yellow thing. Role of thermal interface materials, TIMs. TIMs, also known as thermal interface materials, are used to enhance the heat transfer between components and heat sinks. They fill microscopic gaps, improving contact and reducing thermal resistance. Selection of appropriate TIMs can significantly impact thermal performance. If a heat sink is placed directly on top of the heat generating device, which is a chip, a thin layer of air gaps will exist between the two mating surfaces. As we can see here, there is a heat sink surface and a chip surface, and when you place them one on top of one another, there is a thin air gap present over here due to the roughness and imperfection of the surface. Since these are not very smooth and like very accurate to fit in with one another, there exists some roughness and imperfection. Due to that, air gap is occurred. The air gaps are thermal barriers to the heat dissipation path. Now these are thermal barriers to the heat dissipation path. To remove the reduced air gaps, thermal interface materials, also known as TIM, shall be used between the two surfaces. Good interface material should have high thermal conductivity, good capacity to find out the microgaps, and good long-term stability. Now, without any TIM, the direct contact, you can notice some air gap in there. And with using TIM, thermal interface materials, you can fill up the air gap with those. There are different types of thermal interface materials, and they can be like thermal greases, thermal phase changing materials, gap filler pads, thermal tapes, thermal exposes, gels, solders, etc. Now let us know about the modeling heat transfer. Finite element analysis, FEA, can stimulate heat transfer in complex electronic assemblies. Accurate modeling helps to predict temperature distribution under various operating conditions. This information aids in optimizing design for thermal efficiency. Now let us get to know about the cooling techniques of electronic devices. Various cooling techniques include passive cooling, active cooling, and phase change cooling. Passive cooling relies on natural convection and conduction, while active cooling uses fans or pumps. The choice of cooling method depends on the specific heat generation and design constraints. Thermal testing protocols. Standardized thermal testing protocols ensures the consistent evaluation of device performance. Testing methods include thermal imaging, ambient temperature monitoring, and thermal cycling. These tests help identify weakness in thermal management solution. Now here we have an article regarding this from a newspaper. Now let us get to know about the impact of environment on heating. Now, heating ambient temperature and humidity can significantly affect the thermal performance of devices. Electronics operating in high temperature environments may require enhanced cooling solutions. Understanding the environmental factors is essential for reliable device operations. Now, here we have the graph of relative humidity, temperature, relative humidity, and air density ratio. Air density ratio is get like decreasing, and the temperature degree Celsius is distributed in like a separated way. Design consideration for heat dissipation. Component placement and spacing can influence heat dissipation in circuit boards. Heat sinks and thermal vias are commonly used to manage heat in densely packed designs. Effective design can mitigate hotspots and improve overall thermal performance. Now, let us get to know about a case study of heat management. Several case studies highlight successful implementation of thermal management solutions. Analysis of these provides insights into best practices and common pitfalls. Learning from real world examples can guide future designs. Advances in thermal materials. Research is going on into advanced materials like graphene and phase change materials. These materials offer enhanced thermal conductivity and heat storage capacities. Incorporating advanced materials can lead to more compact and efficient devices. Now, to a conclusion on specific heat estimation is accurate estimation of specific heat capacity is essential for effective thermal management. Through a thorough understanding of thermal properties can enhance device reliability and performance. Ongoing research and innovation in this field will drive improvements in electronic systems. Future trends in thermal management. Emerging technologies such as 3D printing are influenced thermal management strategies. Smart materials and self regulating systems show promise for future applications. The integration of AI in thermal management can optimize performance dynamically. Regulating standards for heat management. Compliance and industrial standards ensure safety and reliability in electronic devices. Regulatory bodies provide guidelines for thermal management practices. Adhering to these standards is critical for market acceptance and consumer trust. Now, let us get to know about the role of simulation software. Simulation software can model thermal performance before physical prototypes are built. This reduces development time and cost associated with trial and error. Utilizing software tools allow for more accurate predictions for thermal behavior. Now, this has a collaboration between engineers and the scientists as well. Interdisciplinary collaboration is key to advanced thermal management technologies. Engineers and scientists can work together to innovate a new material and design. Such partnerships can lead to breakthroughs in heat management solutions. Thank you.